那这个电影，你有可能是很对。You know you can turn on this. You know. You can use so much to control this kid. You can screen so much. Có thể là một công nghệ đồng sự để you know, I want to tell you. Oh, can you scan the QR code? There's the collab link inside. The code link. We only have one. I don't have one more. Okay, we are going to start now. The code will be inside this QR code at the bottom. So just scan the code, then at the bottom of the form will be the code that we'll be using today, this code. Yeah, so just load the code first. Okay, once you have loaded the code, right, I need you to scroll down to here, search for this W2V Queen and go to runtime and run before. So go to search for W2V Queen, then go to runtime, then run before. Then it should run everything up. Like this, you can save some time on running the code. So the code, right, you can just Control F, then search for W2V Queen, which is here. Then you click inside the cell, as in typing inside the cell. Then you go to the top, the runtime at the top, then press run before. Okay. So press inside the code block. Press inside the code block, then runtime on top, then run before. Uh, for her that she just come in, can tell her to scan this code, then the code will be at the bottom.
I'm sorry. I can't seem to find the runtime.
Oh, so that should be at the top here, right below.
Yes,
The
because my
reason there should be
I think
something
on
at the
my
left that like you can
left
open up
hand
or something,
doesn't
I
have
think.
my on top right doesn't have the file edit view at the bars.
Don't have that. Does it look like, if it looks like this, there should be one arrow here.
Did you open with like any kind of software or something? Because I'm using Chrome,
You're using what?
Google Chrome.
I'm also using Google Chrome though.
Wait, let me just try.
If you cannot, then you just okay, the important one, the point of doing this runtime before is that there's one thing that takes very long to download, this one. So if you can't find the runtime, just run this part first. This one, the import gensim, this part. Because it takes 10 minutes to download this one part. This part. Sorry. So you see this picture, the cell below. If you can't find the runtime, just run this block first. Also, if you got questions in the Zoom, just type in the chat. Don't ask me because I shouldn't be able to answer. Okay, but just run this code. If you can't find the runtime, this block, it will take 10 minutes to run. Okay, I assume you all have all done that. If you haven't or still lost, just type in the chat. So to start with some admin matters, this is our group. Yes. Then this will be our future workshops. So computer vision was yesterday. Now we are doing intro to NLP. Then next week, Wednesday, will be CNN, convolution networks, transfer learning, and transformers after that. Even for those that's interested in vision only and here to just listen to NLP, transformers will be very important. Because all your famous models are using transformers. Then hopefully you have some idea of what to do for your project by week 4. So week 5 onwards, have some project consultations. Then week 6 will be detection, segmentation, and prompt engineering. So hopefully at the end of this lesson, you have some direction of where to go for your projects. So let's start. What is NLP? So for those with experience with deep learning, data analytics, or simple CV, the idea behind it very simple. The data just goes into the linear layers and you get some output. So NLP will do the same. We will transform words into letters so we can perform matrix multiplication. But the biggest difficulty with NLP, and the part that makes it difficult currently to this day, is that ambiguities makes it difficult to understand text. So a common example is just words can have different meanings. Like I go to the play versus I play at the playground. The word play can have different meanings and the context will change the meaning of words. So a lot of new releases and new advances in NLP will be to solve these ambiguities in language. So for the benefit of those that don't remember deep learning or are not familiar with deep learning, I'll first recap on what is deep learning. So deep learning just takes matrix multiplication of data you have. For example, house prices or house floor areas, and they will multiply them with variables or what we call weights to get an output. And these will be random at first. So we will find how to change these variables or weights using a loss function in order to minimize this loss. Hopefully this picture can help you understand it a bit better. So we start off with input X. We will input it into a model called F, and we get output Fx of the input. So this Fx will be a prediction of what we want to get from the input, and we'll compare this prediction with our actual answer, which we call the label. So a basic example will be just label minus prediction. So we'll take this difference, which we call the loss, and we use that loss to update the model. And this will be split up into the back propagation, which I'll go through a bit later. So how does matrix multiplication works? So let's say we start off with a 1x2 array, x1, x2, and we want to get an output of size 3, which is h1 to h3. So we have this thing called weights, which are the variables wh. So if you notice, if we multiply a 1x2 matrix and a 2x3 matrix, we get a 1x3 matrix. So this wh will basically be our variables. And h1 will be a linear combination of x1 and x2, and h2 likewise. So using this matrix multiplication, a model will be able to learn relationships between the input variables to get a certain output. We wouldn't go through so in depth, but if you're interested to learn more about this, you can just find out yourself about deep learning. And so this backpropagation will be how we update the weights. In other words, how we update the lines to get the output that we want from the inputs. So this is the basic formula for getting the output, which will be the input times the weights, the red color times the black to get the output, which is the green. So the loss will be or how wrong we are, will be the answer minus our prediction. So let's say we have a graph of our loss against our weights, against our variables. So at the start, we will be very wrong. In other words, our loss will be very high. And we want to bring our loss to the bottom or minima. So we do this by using this formula at the side. The new weights will be equal to the old weights minus the d loss over d weights. And in order to obtain this d loss over d weights, we use this formula. So the d loss over d weights will be equal to d weights over d output. In other words, the derivative of this formula times the d output over d weights. In other words, the derivative of this formula. So basically, these three equations will tell you how the model learns. I won't go too much into math. This is just very basic math, and the loss functions can be very complex. But this is just a simple overview of how models learn. Then I'll recap on the training loop. For now, it's just a big random bunch of words, but later in the code, I'll go through this again. So it's just basically the most important parts are preparing the data, zeroing the optimizer. Okay, so the optimizer just optimizes these jumps. So these jumps can be very slow and get stuck at a point. So the optimizer will optimize basically the algorithm to find the bottom. Then we have the forward pass, which is this matrix multiplication, and then the loss calculation, and the backwards pass, which is calculation of this formula, calculation of d loss over d weight using this formula, and then the step to update the weights. Okay, then now we are finally moving back to NLP. So how do we represent language with numbers? The most intuitive step will be to map each word to one letter. Then we have a dictionary to remember which number is which word. We will be trying this now, so we can refer back to the collab. So the first one is just installing a data set. Don't need to understand this. So back to NLP. So after we have converted the words into numbers, there are a few cases that we can use these numbers for. So obviously the one that we should be the most familiar with, ChatGPT, is text generation. So we try to predict the next word using previous words. But there are other uses of NLP, such as text classification, which we are going to try now. So we use the text to try and predict what kind of sentence it is. For example, in this case, we'll be using news. So we are given a headline. You are told to classify that headline into what class of news it is. In this case, it will be world news, sports news, business news, or tech and science news. Of course, there's other uses of NLP, such as sentiment analysis and name entity recognition, but we're not go too in depth into these two first. So this first code block will be loading the data set. The data set is called AG News, which will consist of news headlines in the following classes. So you can just run, if you're not sure about any code, you can try editing the code and running it yourself. So the example of headlines will be here. If you run it, you should get different headlines because it's random because of this shuffle. So you will not see my headlines, you'll see some other headlines. So first, in order to get like a mapping of a word to a number, we first have to create a vocabulary. Or in other words, the words that we know. So we'll do this by using a tokenizer. Okay, skip this image first. We'll be using a tokenizer to first convert a string in Python, or in other words, a sentence, into its component words. So the tokenizer here that I'm using is very simple. It just converts the sentence into and takes out the words. But the more advanced models like ChatGPT or any other model you're familiar with, we have a more complex tokenizer, such as the image here. So you can see that a word that is not familiar with, in this case, rumination, they will be converted into, they'll be broken down into simpler words. Or in other words, the words that the model understand. So this way, models are able to adapt to unfamiliar words by converting them into their root words. But our model is not that sophisticated. So if I enter a word it doesn't know, all it does is just keep that word. But if you're given a more sophisticated model, you will try to understand this as a typo. In this case, this is BERT's tokenizer, which breaks up words it doesn't know into simpler words that it might be able to understand. Okay, the next step will be counting the number of words in our data set. The reason why we are doing this is that there's some words that are typos in the data set, or there are some words that are unlikely to happen again. So it's very inefficient to keep these words in our knowledge. So we do this by using the collections counter item. You can just understand this as a counter, basically. It counts the number of times a word has occurred. So if you are curious how this looks like, you can actually try to print it, but it will come out as one humongous item like this. So we'll use this counter item to create our vocabulary. And if we print the first few items, it look like this. Okay, mine looks a bit strange because my first news is relating to UK Muslims, but yours should look like something else. So what this means is that our vocabulary will convert the word UK to 0, Muslims to 1, starting to 3, etc. So in this case, our vocabulary has a size of 95,000. So there's 95,000 unique words within our data set. So from this, we first have to know how to convert the words to their numbers, which we use as string to index. So if you want to print this, you'll get a dictionary of words to index. So in this case, for example, UK will be 1, Muslim 2, etc. So we create a function called encoding, which transfers the sentence into these tokens, into their indexes. An example of which will be here, the output of this text. So I'll stop for a while for you to digest what just happened and what happened in the code just now before moving on. You got any questions up until this point? But you understand the basic idea of converting the letters into numbers, right? Should be quite simple until this point. So you can just try out yourself lah, this encoding part. Okay, now I'll move on to the actual text classification part. So now we have a sentence that we're able to convert into numbers. But we want to use this sentence to try and predict what type of news the news article is. So the simplest is called something called bag of words. So this just creates an array of zeros of length vocabulary size. So imagine a 9,500 long array of zeros. Then for each time a word has appeared, we increase that index by 1. So basically this function just counts the number of occurrences of words. So you look something like this. Let's assume our vocab size is just this small. About bird herd is the word you. So for a given input, all it does is count the number of times the word has appeared. So it's just very simple. So hopefully by using this, we can classify what news headline is about just by counting the number of times certain words has appeared. Because the intuition is for science news, maybe the words like Apple, computer, phone will appear more often. And for news articles relating to sports, maybe injuries, competition first will be more common. So we do this by of course, the tokenizer, as said before. Then this part just creates the array of zeros of that length, and it just counts that index by 1 every time it meets that word. So here is back to the idea of converting converting words to numbers again, where the number is the index in the vocabulary. Yeah, but if you still don't understand, it's basically, so let's say I want to convert, I love to play with the words to their indexes. You'll create this, same as before. So basically, the bag of words will output this. And at index 477, there'll be a 1. At this index, there'll be another 1. At this index, there'll be another 1, and so on. So it's just basically counting the number of words that has occurred in a sentence. Very simple. So now we'll move on back into the deep learning part. Of course, you have your data loader. You should be familiar with this if you have done deep learning. Our model will be very simple actually. It's just one single linear layer that converts in this case will be 2,000. Okay, we shrink our vocab size down into 20,000 to make it simpler. Because there will be typos in the news, there will be words that only appear once. So you shrink down vocabulary. So that words that appear, for example, only once will be chopped off. And we forget those words. So our net will be just a very simple linear layer of 20,000 inputs and 4 outputs. So what this will look like is, for example, there'll be 20,000 of these red circles and only 4 output circles. If you can imagine that matrix or this diagram. Then we'll end off with a log softmax that converts the output into a probability of some 1. So in other words, our model will input the number of times each word has turned up in a sentence and output the probability of it being in each class. So in this case, there'll be one circle, another green circle at the top. That'll be the probability of it being, for example, world news. Then the second green circle will maybe represent the probability of it being sports, etc. Then back to here will be the main training loop that you see in most deep learning tasks. So in this case, it will be similar also. You start off with text. We're preparing the text by separating the data in the data loader into their text and the label, which is what we want the prediction to be. Then we will zero the optimizer. So in other words, this optimizer just updates the weights from the loss. You want to zero this, because at every loop, the optimizer will hold a value to update the weights by. So we zero it at the start of the loop so that the next loop, it can update properly. Then this is the forward pass. In other words, this function of matrix multiplication. Then we calculate the loss. Then we do the back propagation, which is this step. Then after that, we just update the weights using the optimizer. So this part is standard. It will be the same as other deep learning tasks. Just, yeah, there'll be not much differences. Then the code below this part is just calculating the accuracy and the loss. So if you run this, the accuracy will start at a low amount, then will slowly start to increase, showing your model is learning. At the end, you should get around 0.8. And you can try your model now. So the model is basically trained. That's it for text classification. Very fast, very simple. And if you can try any news, you should be able to get the probability of it being each class. So in this case, I use very sports-like words. It will result in a high probability in the sports category. So once again, each number just represents the probability of it being in each class. And the classes are at the top here. The first number will be world, second number will be sports, third will be business, and fourth is science and tech. So I'll take another short break now for you to test this out. And if anyone got any questions. You got any questions? Okay, good. Everyone understands. Yeah, but those on the Zoom, if you have any question, just type in the chat. There'll be someone to help you. Sorry, can you repeat? Yeah. Okay, so the question I got was in the dictionary we train, or in other words, the vocab, the words are only in the data set or every single word. So in this case, it will be only for words from the data set. Cause, wait, is it? Cause over here, we created a counter of number of words. So basically, we counted the number of times each word has appeared in the data set. So basically, these will be our entire vocabulary. In other words, our model only knows words that occur in the data set, the news. So first we take the words and we convert them into numbers. This part, okay? Then next step, we count the number of times each word has occurred. So then basically the model learns from this. So maybe it can learn that the word like soccer might mean that it's most likely to be sports, then etc. As to how the model learns, right, or what the model learns, we're not really sure because it's a black box. It's just the math. Sorry. Yeah, but it's just the math. The math helps the model learn. But what the model learns, we are not sure. Like for example, it might just count the total number of times soccer plus basketball plus etc. Count, then they do some function that turns it into a probability, but we're not sure what it does lah. As in like what? Okay, the way you can think about this is that the model learns what pattern to predict by itself. We don't need to teach it. It will do it by this math, by math.
How the words converted to numbers?
How the words converted? Oh yeah, you came late. So the words are converted by numbers. Firstly, by using a counter. So you count the number of times the word has appeared in the data set. So for example, where is it? So for example, the word the has occurred this many times. So we take the top 20,000, we chop the rest off and create an array basically, where the index is the number the word is represented by. So for example, this case, the number 0 will be the full stop. The index 1 will be the, etc.
Semi-order.
Yes, but it will likely be shuffled below lah. Just to let you know. So in this case, 0 is represented by UK, or UK is represented by 0, Muslims by 1, etc. So you can try using this function to change the words into letters. Still any part you're unsure about? But don't worry too much about this the code inside this loop, because it's standardized. Almost all deep learning stuff will use the same commands. Optimizer dot, like this part, almost all deep learning tasks will use the same code. Okay, so recap of what we just did. We map each letter to one word, map each word to one letter, keep a dictionary to remember which number is which word. And we use the bag of word to keep tracks the number of occurrences of each word in a sentence. Then we just use linear layers to find a pattern in number of occurrences of the word and the class of the news. So one possible question some of you might have but haven't asked yet is that why do we use the back of the words? Why you count the number of occurrences of each word? Why not we just input the tokens, in other words, the numbers? Sorry. Why can't we just input, where is it? Why can't, why can't we just input these numbers into the model and let the model figure everything out? So a few problems. The biggest one is that if we do this, the input will be of variable size. So as we know our so as we know our model will be size 20,000 inputs and 4 outputs. If we were to input sentences, they wouldn't have a size of 20,000. So that's problem number 1. Problem number 2 is that these numbers have a very, very large range. So the weights in the middle will be very disorganized. The word for this, if I'm not wrong, is called sparse representation. If you are curious to learn more. Yeah, but if you're interested to know more, is about this thing. So put simply, it's just that if you have an input of a very large range, such as like 17 to 20,000, the model doesn't learn very well. Okay, so now I'll move on to the second task, which is using a latent space of n dimensions to represent a dictionary where points are numbers. So this sounds very complicated, but put simply, it's just this. So we have, for example, we have an XY Cartesian plane. And as you know, there's infinite points because there's infinite decimals. We can use a point to represent a word. For example, like technology may be a point in this Cartesian plane. And we can go one step further by giving meanings to this axis. So for example, the x-axis can mean like how masculine or how feminine a word is. And the y-axis can mean like how tech-related this word is. So you can expand actually from an xy axis into multiple dimensions. So xy is just 2 dimensions. And maybe it can hold maybe 2 meanings, for example, the masculine and techness. And we can expand this to multiple dimensions. Like I give you an example of a very well used and very good embedding. Is this by OpenAI, and it has 1,500 dimensions. You can imagine XY is only 2. You can imagine how large this is. So we'll be moving on to the collab to try to implement this. Sorry? What do you mean by each feature you have? Each dimension. But basically, yeah. So instead of turning a word into a letter, which we've done before, we will turn it into an array of size 1,500. And that's what they do. So imagine one word be converted to one very long array. Yeah, you'll try to learn what each value is the best. Later, I'll give an example of the result of this. So we'll continue from after these interpreting results to embeddings. So I said the idea of embeddings will be to represent words. You can read yourself. There's two ways of training such an embedding layer. Because at the end of the day, we want the embedding to be able to learn the meaning of the words. Because the problem with back of word, sorry, not back, the back of words we learned previously is that the model doesn't know the meaning of the word. It just counts the occurrences of each word and try to deduce the class from that. But now we want to teach the model to learn how the meaning of each word. So you can train this by using something called a back of words model, which just does this. So how this works is just that it trains a model to predict the middle word given surrounding words. So for example, given 5 words, it will cut out the middle word and try to predict the middle word given the surrounding 4 words. So for example, is this, I am running to school. So what the model does is that, oh, sorry, not what the model does. So when training the model, we'll chop out the middle word and try to make the model predict this middle word given the 4 surrounding words. So once we have trained this model and we have inputted I am to school, words with similar meanings will have similar probabilities. So the output of the model will be a vocab size array, and each number will be the probability of that index being the middle word, if you can understand. So similar words, as a result, will have similar probabilities. So in this case, if I inputted I am to school, running, jogging, walking should have similar probabilities. So this is how the model learns the meaning of the words. But we will not be trying to train a new embedding layer because English words can only have a fixed meaning and they're unlikely to change. So there's not much point in training a new embedding layer when you can use what other people use. So hopefully your word to vec, which is an example of a back of word model, should have downloaded. It takes 10 minutes to download. That's why at the start I asked you to download first. And you can try to test it out by testing similar words. So in this case, if you input the word neural, you'll find similar words such as neurons, neuronal, basically brain-related stuff and words related to neurons. So this is what the model thinks are words that are similar to neuron. And what is cool about this embedding is that you can perform vector addition, vector subtraction on words. So for example, the example given here is king, woman, man. So if you take the embedding of the word king, okay, it will look something like this. In this case, this is the 300 dimension embedding. If you take the length of this array, you'll get 300. So you take king minus man plus woman and convert the embedding back to a word, you'll get queen, which is very interesting. And research has been done upon this, but back to the concept that the meaning of the word will be represented by the axis in the embedding. So for example, the axis can be male, female. You'll get results such as king and queen being at such positions. So you think king minus man and plus woman, you'll reach this point. And you can try it out. You can try it out. Try this out yourself. Like maybe you can take king minus royalty. Then maybe get a prince. Because if you take a king, you remove his royalty position and he's just a prince. If you think about it. Right? Because the prince is just a person that has not become a king yet. But you can try this out yourself. Maybe you'll give some funny results also. Because this is just what the model learns. We can't control what it learns, but this is what it learns. And once again, here's an example of what queen will be represented by, and we take the length, you can see it's a 300 long array. So this is back to your question previously about what the word will be represented by. So comparing back to just now we are converting a word into one number. Now we're converting one word into a very long array. Another way you can think about this is that each number here represents a quality of the word. So for example, this number may represent how feminine or masculine it is. So a high number can mean the word is more feminine, etc. But obviously we don't know for sure because how the model learns we can't control. Yeah, and comparing again, this only 300 dimensions. Then as we know from just now, the OpenAI's one has 1,500 dimensions. So of course, more dimensions will mean the model can understand the meaning of the word better. Yeah, so so you can look at other examples of when people try to visualize what the result of this is. Like there'll be a certain distance between the country and a capital. Actually, I haven't tried this out yet. What if you take a capital? You take a capital, for example, Ottawa. You can spell it. Then we minus away Canada. And add Japan. Yeah, you'll get Tokyo. So in other words, you'll take one capital, minus away the country, and add the country, you will get the capital of the other country. But back to how it learns this is just back to this. It tries to predict. So for example, the capital of Japan is Tokyo. Then it just learns that when it is something else, it should be something else. Yeah, but feel free to try this out. This is quite interesting. Well, we are early by a lot. So anyone got any questions can just ask. So far.
Sorry. So let's say earlier example, like you put the Ottawa into
Yeah.
Singapore. Then will it give out like Singapore again? And will it refers to the same Singapore or the different one?
So here. We do have this part running. Is it you haven't downloaded yet? Oh, but now you use Hong Kong. Oh, yeah, but it takes very long to load. That's why at the start I asked you to load first. But you can try out. You can search this thing called word2vec online. There's been research done on how the model learns. Like this is the result of one of the research. Because once again, I must remind you the model, we can't control how the model learns. I know we can control how the model learns, but we can't control what the model learns. So we can't really know what the axes are. But we know there is something. Like in this case, it will be country capital. Oops. Anyone got any other questions before we move on? Okay, now I'll move on to contextual embeddings. So just now we have talked about the problems of back of words, which is just that it counts the number of words and doesn't understand the meaning. There's another problem with this word2vec model, which is that it doesn't take the context of the word into account. So once again, earlier I used the example of play. These two examples, the word play have different meanings. So if we use the earlier word2vec, the word play can only be converted into one single vector of the size 300. So it's unable to capture the other meaning of play. So to solve this, computer scientists has created something called RNNs. Okay, by this point, you should reset your runtime. But if you want to try, of course, this one, then you can't. But at this point, if possible, you should reset your runtime. So you just press run, go back to runtime, then restart. Restart runtime. Or you can refresh it, it should work also. Okay, the reason why I asked you to reset is because there's some compatibility issues below. But if you don't want to lose your progress, you can try starting a new tab, but I don't think it will work because Google Collapse places a limit on how many instances you can have running. If you don't reset, if I'm not wrong, if you run these two, there will be some error below here. I mean, you can try, because if I am not wrong, there should be an error here. Okay, wait, I'll check out the text first. I'll check out the online if there are any questions first. Oh, the online people got no questions. Okay, good. Okay, while this code is running, I'll talk about the RNNs. Okay, this part is a bit complicated, I have to admit. It's a bit complicated to understand, but no choice. This is an important architecture that solves the problem of non-contextual embeddings. So just now, the order of the words didn't matter because there's no I don't know how to explain this properly. There's no order into the model. So people have invented this thing called RNNs, which do. This image a bit hard to see, but let me copy into the slides. So this model just looks like this. So one way you can understand the architecture of this model is that each cell converts the meaning of the word. So it takes in the word and the previous words and output the meaning of the previous words. So maybe, for example, this RNN cell number 2, it takes in the meaning of the previous words represented by S1 and also input the current word and outputs the meaning of the previous words combined. So this way, there's an aspect of order where words are added subsequently into the meaning of the words. As for what inside each RNN cell, it looks like this, but I don't really have to understand it because PyTorch does it for you. So yeah, you will look, I have this slide, never mind. Yeah, so S1 will be the meaning of previous words. Then it just appends the meaning, similar as to how the C bag of words work. Yeah, so the final output will be the meaning of the whole sentence. You can understand it like this, because it will also be a very large dimensional output. And then you'll go through a dense layer, which is just the linear layers, to learn how to classify or predict words based on the final meaning. So the code should actually have an example of how this works, which is here. So once again, you input stuff, then you create it's the same data set, the AG news. You build the vocab, create the counter once again. Then here we have the RNN classifier. And so the embedding this time will be different. We use Torch built-in embedding, which we were trained from scratch, I think. Then here is the RNN. So the RNN will input the embedding dimensions. Or in other words, in this case, I'm not sure how many dimensions this is, but previously it was 300. It will output a hidden dimension, which is the dimensions of at this point. Then the final meaning of the sentence will enter into the linear layers. So similar as just now, we have a data set. Similarly, we have encode. We just turns the words into the letters, into numbers. Then this is the training loop. Once again, we have the same shape. We have the optimizer once again. We have the forward pass once again. Then loss, backward step. Yeah, then after this, similarly is the calculation of the loss. Okay, there's a problem now that I have loaded the wrong collab runtime, which is a CPU runtime. So give me a second. And recap for those that never come for our earlier workshops, the CPU versus GPU. If you don't know what the differences between these two are, basically GPU runs AI code faster. That's why NVIDIA stock rise so much. The specifics, you can Google them yourself if you're interested. So this will take very long to run. And before that, yeah, so the training loop once again, then here with the Pedify. So the problem just now that I explained about inputting words into a model directly is that the sentence might have a varying length, but the model has a set length. So the model can only take in a sentence of length X. Like for example, ChatGPT, you've probably seen the words context window. So that's the max. But for LLM such as these and RNNs, they will pad the remaining parts that you have unused. So for example, the max length that I decided the max length I can take in is 32,000 tokens or words. If you give me, like, for example, a 5-word sentence, I will pad the rest with zeros, for example. So this way we have a constant length that goes into the model. Yeah, so in this case, you will pad this many times with the value 0. Yeah, and basically that's the reason why you see like ChatGPT context. You'll see this word. So basically, whatever sentence you give ChatGPT, it will pad the remaining up to this many words so that you can go into the token. Okay, so the RNN is training now, but for some reason it receives less accuracy than previously, somehow. But yeah, but this is how you train a RNN. Next, we'll move on to LSTM. Oops. So the RNN once again got another problem. If you notice, there's a pattern here. There's every single architecture has a problem. For RNN is something called vanishing gradients. You don't have to understand too in-depth about this. But put basically is that RNN remembers everything. So if you want to get the model to learn, it's not very easy because it learns everything. Then the stuff at the earlier part is forgotten. Because if you learn information theory, you will know that a set number of bytes can only retain a set number of information. So if your sentence is very long, as the meaning goes through it, you'll lose the meaning at the front. So it wouldn't update properly, basically. So once again, people made a complex thing called LSTM, which is long short-term memory. So an RNN looks like this. The LSTM looks like this. It's a lot more complicated. But basically, the important part is that it adds a forget gate, input gate, and output gate. This forget gate allows the model to learn what to forget, basically. And once again, it's another case of we can't control what the model learns to forget. The model will learn it itself. So we won't go too much into these two architectures. But here's an example if you want to try of using text generation. So previously, we have done text classification, which is AG news. We input the headline and we output the class of the news. But now that we have stronger architectures, we can try to generate text. So basically something like ChatGPT. Yeah. So once again, we'll do the same thing. Create the tokenizer, create a counter, then vocab size once again. Then again, we have the encoder, which they have the same encoder. Converts the letters into numbers. Actually, before I move on to text generation, let me have a check that you all are doing okay first. You all any questions? Which diagram? Okay, honestly, right, I tell you straightforward, very straightforward. You don't need to know. Because this was invented, I'm not sure how long time ago, and you probably heard this word called transformers. Transformers replaced this LSTM. Yes, quite a long. In 2018, I think Transformers replaced this LSTM. So LSTM replaced RNNs. I'm not sure when. Then more recently, Transformers replaced LSTM. So LSTM also has a problem. it lacks attention. Basically, I'll explain next session. Someone else will explain next workshop, because the next workshop is called transformers. As you know, transformers have replaced LSTM. The reason why I'm teaching you this thing regardless is that it's a bit embarrassing lah. If you go through this, then you don't know what LSTM, you don't know what RNN is. End of the day, these are still like very big steps in the history of NLP. Like I can say that these two architectures are not really useful, but when they were created, these are like revolutionary. So you still have to know. Okay, but basically the diagram is hard to understand lah. But basically it's just an RNN, but they add three things: the forget gate, the input gate, and output gate. So these gates just give the model options on what to do. So like I said quite a few times, we can't force the model to learn our way. The model will learn by itself using the math. And at the end of the day, it's still those three formulas in backpropagation that makes the model learn. But adding these three gates allows the model to forget stuff and retain information. That's why it's called long short-term memory. It's able to forget things it doesn't need, so the information is carried through. But once again, not very important, because you're unlikely, honestly, you are probably never going to see these two architectures, because transformers is just so much better.
Okay, transformers.
You will learn next workshop, but we can have a preview of the transformers architecture. So transformers, you'll probably hear this paper if you mention transformers, it's called Attention is All You Need. It's a paper made by Google's AI team. And basically it just adds attention into the model. So it looks like this. The transformer model looks like this. Once again, I'm not going to go too in depth, but to simplify what this does, right? It allows the model to control the intensity of the embeddings at each position. So for example, once again. So for example, I convert these words into their embeddings, right? Then I don't use embedding, I use just tokens. So for example, I convert it into this 1, 2, 3, 4, 5. So the transformers allow each word to control how much it is influenced by other words. I'm not sure if you can understand what I'm saying, but we'll go through more in depth next workshop, so don't worry. But basically, it just lets the model learn to pay attention to each words. That's why it's called attention. But don't worry, next workshop, we'll go through. And you'll probably see this one actually, attention mechanism. Yeah, don't worry about the French. It's just because these stuff are invented by papers. Like research papers brought forward these ideas. And just French is just what the original paper used. For example, transformers was used in machine translation. So as you can see, this is what attention does. When you translate "Are you still at home" to French, which is the top column, it makes the model pay specific attention to certain words. So for example, translating the word "at," it pays especially attention to the word "casa," which I think is French for "at" or something. Wait, isn't "casa" translation of home? Yeah. Yeah, casa is at home. But I think if I'm not wrong, the model just pays attention to the word "at." Because the word "at" influences the meaning of the word home. But it's back to the idea of context again. But don't worry, we'll go through this next week. So let's not rush. But back to text generation. Yeah, casa is home. Casa is home. So text generation is similar to text classification. So for text classification, the output will be a size 4 array of which class it is, correct? But text generation will be a vocab length size array. And each number will be the probability of that word being the next word. So how it trains is that it takes, for example, let me find the AG News example again. So for example, you have a data such as in Michigan, criticism grows over Toronto's export. So you will first input these three words, then you will try to predict the next word, which is grows. Then after that, you input these four words and try to predict the next word, which is over. Then after that, once again, it predicts until includes this and tries to predict the word Toronto. So basically, this is how text generation training works. This is how ChatGPT learns. It tries to predict the next word given previous words. So it's quite intuitive actually if you think about it. So how ChatGPT works, right, is just that you input text. For example, what I don't know what. For example, I ask ChatGPT what are transformers. Then you take this word and try to predict the next word. But since there's a question mark, you'll know that the next word should be an answer. So basically, you'll predict one word, then you'll take the next line and predict the next word. Then it keeps on doing this for every single word. So it's actually a very step-by-step process if you think about it. Okay, so back to the RNN. Let's see how the training is going for the RNN. So here you can see these models attempt at learning text prediction. At the start, right, it doesn't learn very well. If I input the word today, it will just spit out this. But as it slowly learns, it will start making some sense of the words. So basically the model has learned that after the word today, the word and is the most likely to occur. Then after the words today and and, the next most likely word to appear is a. So basically, it just keeps doing this until you want to reach a set sentence. Yeah, so as the model learns, it will slowly make more sense. But this data set is not very good, so the model won't learn very well also. Yeah, but basically, this is how just text generation works, although it's using LSTM, which is not very good. I think in transformers, you'll replace this with a transformer model, and you'll see the difference. But basically, this model sucks. It doesn't predict words very well. So until this point, got any questions regarding text generation? But this is just a sneak peek. We won't go next session. I think that you'll go more in depth into text generation because this model legit CMI. Any questions? Okay, wait, let me check the Zoom chat. Name error char tokenizer is not defined. This one. You try restart and run everything, or you try restart the runtime and run the cells again. Not sure how you're getting this error.
I think that's the child organizer.
Yeah. Okay, I'm not sure, but the block with the char tokenizer definition isn't char tokenizer. Oh, I have it here though. It should be here. Oh, you also face this error. Oh shit.
It's not there in the notebook.
Okay, it's over here. I think the notebook never saved properly. Do you have these two blocks? Oh.
No, it's not.
Let me try to remedy.
The architecture picture. It's directly the last LSTM.
Oh, so after this picture, there's no more.
See the LSTM summary.
Okay, let me save again. Wait, let me stop this. Wait, I can't interrupt it. Never mind. Let me double check if it's updated. Okay, try refreshing it. Try refreshing the notebook. Wait, it's still wrong. It's still not updated. Yes, most probably. Let me. Uh, okay, scan this, try. If you all got Telegram web, I'm not sure how you're gonna put it into your phone, into your computer, but like WhatsApp yourself, Telegram yourself, voice email yourself. Okay, but yeah, this version should be the correct one. Wait, for the Zoom guys, actually, wow, I forgot about you guys. I can actually put it in the chat. Okay, but for this, you should start running after this part and make sure you are using GPU. So you start after this pip install portal. You should go to change runtime type and go to select the GPU. Then start running after this. If you face an error here, you go runtime and restart runtime. The error should disappear. Then after that, run everything. What? Got a problem in the chat. Still don't have runtime. Wait, for those that are not facing runtime, are you seeing something like this? Can the person in the chat let me know? Are you looking? Do you see something like this? Yeah, then it's the top right. There's the arrow. This arrow. Can? Yeah, but only reset the runtime if you're facing an error here. This cell might have an error, then you need to reset runtime. But otherwise should be okay. But make sure you're running GPU otherwise. Yeah, and after the last cell is run, right, you should be able to try out the text generator. Uh, oh. Okay, I don't know why this doesn't work now. I wanted to try giving an example of how this text generation work, but seems like I don't know. Yeah, but the session more or less over. But if you want to stay, then stay, I guess. But I don't know what I can't get the prediction to work. I wanted to show you all how the but that's just the model trying to predict words after the word today. Okay. Hang on. Yeah, but anyways, this model is tiny. That's why the output looks like shit. But stuff like OpenAI, I have no idea how many parameters that is, but most working LLMs have like 70 billion parameters. 70 billion. This one has like a bit less than 10,000, I think. You can do the math lah, cause it's just, honestly, I'm not sure how many dimensions this is. But I think confirm less than 1 million, because else it's not this fast. But the real workings one have at least like 70 billion parameters. So like the parameters, by parameters, I mean like these lines. There's 70 billion of these lines altogether. Then for actually, right, I can prepare you all for next. Okay. Each line is one. Oh yeah, yeah. If I'm making it simple, I excluded bias, but yeah. I can see if I got the. Okay, actually, I can give you all an example of what we are doing for prompt engineering. So if you create a OpenAI account, not the ChatGPT account, the OpenAI account, you'll get free $5 of credits. API credits. Do you know what's API? Yes, I don't know, something like this lah. But basically, you can query OpenAI with an API. You get an API key lah. You need to find yourself. Don't use mine. Then you can. Never mind, I'll delete the key after. Then you can, for example, query ChatGPT like this. Like you want to query how do transformers work, then you'll give something like this. But in this case, it thinks it's the electrical transformers. But it's literally just ChatGPT, but text. Oh, I don't have enough money for 4. But if you're all interested, you all can buy 4. Then try to run. If I'm not wrong, if I run now, you wouldn't let me. Because you will say, you should give a 404 error. Sorry. Yeah, I'm not allowed to use it. Let me check. OpenAI. Yeah, but these are the paid ones. You need. Oh, they never say the pricing, but these are the paid ones. Then this, if I'm not wrong, yeah, this is also paid. This is text to image. Then text to speech. Then whisper is speech to text. Yeah. I think it's a very old thing, because I also never heard of text to speech. Yeah, when it's a speech to text, whispers one is quite good. Then once again, the embeddings. Yeah, then this is the dimensions again. Just now we had a 300 dimension, then OpenAI uses 3,000, almost more than 3,000 large dimensions. Then I think this is the old ChatGPT. Try if it works. Oops, doesn't work. Never mind, cannot. Seems like I can only use ChatGPT 3. Yeah, but on prompt engineering, actually, since we have time, right, I can talk about this a bit before the prompt engineer. I'll just give you all a taste. So just now in the slides, oh yeah, the Zoom guys, you all can leave if you all want. We technically finished already. I'm just talking more stuff. So we have an ML model called F, right? New slide. So basically, text generation, if you all remember what I said just now, is just probability of next word given previous words You're just doing this, right? Then equals that humongous array of probabilities. So there's two ways to change the output. Obviously, you change P, right? Or in other words, you retrain the model. That's how you change the output. The easier way, you change previous words. So that's basically prompt engineering. So I don't know, you all heard of prompt engineering, right? What do you think of prompt engineering? Right. Right. No, but prompt engineering is really a very serious thing. So in the workshop thing, we'll be teaching you LangChain. Is for prompt engineering. So you all think like prompt engineering is just like anyone can do things, but it's manipulating these previous words in order to change the probability is actually very important. Because there's recent stuff such as it's called Voyager. Okay, so a build-up of prompt engineering is something called agents. So agents is basically an LLM that can perform actions. The simplest is ChatGPT's one that can read files, it can run code. Have you all tried before? Okay, but this is a paid. Okay, let me show you all. Don't see my stuff, but I have GPT-4. Okay, let me hide my code. Let me hide. So you can. Oh yeah, I should stop recording. Okay, sorry guys. Sorry Zoom guys. And